Okay, let's talk about this lesson 7. And briefly discuss the assignments. Shop 7. And our objective is to deal with orthogonal functions, with the concepts of orthogonality, to understand how orthogonal functions are the results of the solution of certain differential equations. Okay. In general, differential equations governed by Hermitian operators generate those orthogonal functions. Orthogonal functions are very important in engineering. Okay? You can solve problems subject to certain differential equation by finding the eigenvalues and eigenfunctions of differential equation and decomposing the solution into those eigenfunctions. So this is very important. Okay? We are going to talk about some concepts that show more or less how eigenfunctions can be generated. So we're going to talk about some of those concepts in this class. This is the objective here. I hope you guys translated, right, with the translator. Yeah. You did already? Okay. So there's some concepts on linear differential operators. In general, you can an eigenvalue differential equation can be written in this form in general. Okay? L is a linear operator of order n, something like this. And these are functions of x. So the exponential coefficient in this case are functions of x for the operator. And dn is n order derivative. Okay? So L uses the action of several differential operators on U, which is a function of x. Alpha is called the eigenvalue of the differential equation. In general, when you solve a problem, you don't know the eigenvalue. Eigenvalues are obtained when you solve a boundary value. You solve the equation subject to boundary conditions. So eigenvalues appear as a solution of those. W is called a weight function, okay? Which in general are real function. In general, those are real. Real coefficients in general. Okay? Standard engineering problems, physics problems. These are in general real parameters, and W is a real function called the weight function. Okay? So several equations, differential equations, can be cast into an eigenvalue equation like this. Several equations, engineering and physics. Several well-known equations. One of them is the Laplace equation that describes a potential function in a closed domain. Laplace equation in 3 dimensions, something like this, for a function f. We have here Laplace equation in 3 dimensions is something like this. Let's say the function is phi. It's a sum of partial derivatives like this. So this is not an eigenvalue equation. This is a Laplace equation. But in general, you can search for solutions which are the product of 3 functions of a single variable. Okay. And when you work this out, we are going to find equations that fall into the eigenvalue equation that I showed before. So we solve for each one. Okay. So Laplace equation can be solved, and ultimately you fall into those eigenvalue equations. Helmholtz equation also as well. So we have something like this. Very similar to Laplace. With the addition of a term here, k squared phi equals 0. This gives the, let's say, coordinate dependence of waves in 3D space. When you also break phi into 3 single variable functions, each differential equation, each unit dimensional equation is going to be an eigenvalue equation. And you find those eigenvalues. And so on. I mean, the Schrödinger equation, time-independent Schrödinger equation also, that governs problems in quantum mechanics, also has those, can always cast into, eigenvalue equation. Some important thing, concept is what is called the adjoint operator. If you have an operator that is given like this, okay, let me increase a little bit so it's clear in the video. So I have an operator like this. Observe that an is a function of x, and the derivative operator is on the right of an. Okay, the self-adjoint is obtained by inverting the position and putting a sign factor in front. So that's an adjoint operator. It's the L dagger. Okay. So I have a minus 1 to the n's. So I have a little difference. And now we have an to the right. So it means that the differential operator is going to act also upon an. So if you operate this on a function u, you're going to have something like this. Any other derivative applied to the product of an, which is function of x and u. Okay? So adjoint operators are constructed like that. And one important type of operator is self-adjoint operator. An operator is called a self-adjoint operator if it satisfies this relationship here. So L applied to U is equal to L dagger applied to U. Okay? So it's not all operators that satisfy this. But it's only a limited class. This limited class is called, of operators called self-adjoint operators. If we have, in fact, for physical problems and engineering problems, the differential equations are generally at the most second order. Okay? So we can write in general, let's make a particular case for the second order operators. We're going to have something like this, right? According to our model. A0, second derivative, A1, first derivative, A2 function applied to U, okay? And if we, the adjoint operator applied to U is something like this. Observe the change in sign in the second term here because the minus 1 to the n, right? And observe that now I'm operating on A0 and U. So the condition, the adjoint operator is like this. The condition for the operator to be self-adjoint is that those two things are equal. And you can show, if you through the algebra, some manipulation, you can show that this can be satisfied if the derivative of the first coefficient is equal to the second one. Okay? So every operator written like this, such that the first term has a derivative equal to the second one, is self-adjoint. This can be anything. Okay? There's no restriction with two, only the relationship between those two here. Okay? So this is one of the questions in the assignment that we're going to work out. Okay? We can always, if the operator is self-adjoint, you can always write the operator acting on U, actuating on U, in this form here. Okay? Because if we work this out, it's going to be that the first, P is the coefficient of the second derivative, and the derivative of p is the second coefficient. So you can always write like this, in compact form. So this is very useful in understanding the several differential equations that we work along in engineering problems and physics problems. Okay, let's go on with some concepts. The dot product in the space of functions, function space. If we have an equation governed by any order operator, but we're going to talk about second order, but it's something like this. Just recall that our equation is something like this. RTC is doing that today. It's behaving funny. I don't know why. Maybe I thought there's something here. Yeah. LU plus eigenvalue, weight U equals 0. Okay? So for this type of differential equation, U is a solution. We say that a solution in the, what is that? A radial menu. Okay. If the solution is in an interval A, B, okay, if X is in interval A, B, we say that two solutions are orthogonal if they, we define the scalar brackets, the dot product, okay, of two functions by this relationship. A is U conjugate, U and V can be complex functions, okay. The differential equation might be real, but the solution might be complex. You might, for instance, combine solutions to make complex functions or to make real functions. You can always do that. UV times the weight function of the x. That's the definition, okay, of the dot product. So if I have VU, we have observe that if I make the conjugate of this one, W conjugate is equals to W because W is real, okay? So it's going to be which is equals to UV. So I have this property, okay? If we change the position and calculate the conjugate, you have this property, okay? Okay, so this is a concept, okay? Scalar product is very similar to the concept in vector space. The dot product between two vectors gives an idea of the similarity of those two vectors. If they have a projection which is not zero, one on the other. Okay? Two vectors that have no projection on one another have a dot product which is zero, orthogonal vector. I have all these concepts. But the same thing you can do in space, function space. So then we get to the concept of Hermitian operators. Okay. In general, as I said, the physical problems, engineering problems governed by differential equations of this type that I've been discussing. They are always in a domain between A and B. And when you have a self-adjoint operator, and the interval is AB, and if the solutions, two independent solutions, a second order differential equation has two linear independent solutions. Okay? If they satisfy this restriction here, in the boundaries of the domain, okay, this combination equals, these operators are going to be called Hermitian operators. Why are those important? When you have Hermitian operators, they have very important properties. The eigenvalues of Hermitian operator are always real. For instance, eigenvalues in Schrödinger equation might be the energy levels of atomic system. They they are real numbers. It's important to know that, right? Energy is something real. Okay, it has a physical meaning. So every time you have an emission operator, in other words, self-adjoint and satisfy this boundary condition here, this type of boundary condition, there is going to be always be an emission operator. First property, all the eigenvalues are real. Second property, the solutions obtained for a given eigenvalue are orthogonal functions, in the sense that the dot product between functions, function space of different functions associated with different eigenvalues, these are called the eigenfunctions, is always going to be 0. Different eigenvalues, different eigenfunctions, dot product in the function space is 0. Okay? And also, at last, not least, the eigenfunctions of our emission operator always form a complete set. We are going to see what is a complete set. Okay? So we are going to define what is a complete set. What is a complete set? This is an important concept too. In this table, we have some typical functions used that we find in physics and electrical engineering and engineering in general. The parameters that appear in those equations. Okay, those are the parameters that appear in the operator and the domain and the weight function, so forth, and eigenvalues. The Legendre equation, which appears in solving potential in a spherical system. Okay, it appears also in Schrödinger equation, part of the solution of the Schrödinger equation. We have a Legendre equation. So here is the function. These are the functions that appear in the operator, in a self-adjoint operator, which is emission. Okay, 1 minus x squared, 0. Eigenvalues, L is an integer number. Eigenvalue always form a discrete set if you have a limited size. Okay, the distance between eigenvalues is a regular distance in general. But notice that if I increase the domain, if A and B becomes larger and larger and larger, in other words, if the distance between A and B starts to be larger and larger, if I start to make an infinite domain in one direction, for instance, then the eigenvalues start to get closer and closer and closer to the point that you form a continuous set of eigenvalues. Okay, so you can have that too.
Q of x in the second and third column, is that represent A of x?
Qx.
Yes.
This would be A0. Q. Which one is Q? Let me see. Q is something that has no importance. That's the one I mean. P is A0. dp dx is A1. And Q is A2 in the operator. Okay? Okay? So this, I mean, there's no restriction on Q. I mean, Q can be anything, but in a Legendre equation, Q is going to be 0. These are the interval, the solution of Legendre polynomials of order L, with L an integer number. For instance, P0 is a constant, is 1, between -1 and 1. These are the. We have associated Legendre polynomials. There are 2 indices associated with it. Okay, an integer L and the m that goes from -L to L. Chebyshev polynomials use it for filter synthesis of filters. You can make broadband filters. You know, you synthesizing the parameter as a Chebyshev polynomial. Okay. Bessel functions, you can find Bessel functions solving the propagation of modes in an optical fiber, the transverse profile in a cylindrical fiber, cylindrical cross-section. You are going to find Bessel functions. Interesting is that these functions are orthogonal, provided you write like this. Okay, this coefficient here is the nth root of the Bessel function of order n. So we have to find the roots of the Bessel function to build the orthogonal set of functions. one of the assignments for you guys is going to be to construct a set of roots. Because to construct the functions, I have to find the roots. Okay? We have to make an algorithm to do that. I have to make a procedure. Harmonic oscillator equation, which govern the solution Fourier components of a function. You can see it that way. Okay, so we can form a basis of orthonormal or orthonormal functions. Even if the function, it's supposed to have two functions that are generated a solution of those differential equations, those emission operator equations. Okay? But they are not normalized. They are not normalized. So it means that the dot product between two functions is not, this is a canonical delta. It means that it equals 1 if the index are equal and 0 otherwise. The dot product might be different than 1. Okay? Normalized. You can construct normalized functions simply by dividing those functions by the root square of this parameter. Then you have the dot product between two functions like this is going to be always going to be 1 or 0. Okay. Interestingly, is that you can ask yourself, well, give me the properties of vectors that we have in 3D space, right? In 3D space, I can always say, or in n-dimensional space also. But let's talk about the physical space that we are use it. If we have a vector, we know that we can decompose, let's say, in 3 dimensions, right? As a linear combination of unit vectors that are orthogonal. It's not eyes, yeah, sorry. This is a scalar projection. This is the nth basis vector. Two vectors are orthogonal if they satisfy an orthogonality relation like this. Right? That's very easy. Two vectors are orthogonal if the dot product between those vectors is 0. Right? So I use that to decompose. How do we find the coefficients? You use this property. We make the dot product with one basis vector. Or it's the same thing as this, right? The dot product in vector space is size of A, size of AM, which is 1, cosine of the angle between the vectors. That's what is the dot product. I'm just making symbolically here, okay? I'm using the same notation here. So if I do that, this is going to be simply changing all the time. Some shortcuts that I don't know here are happening. So this is the same thing as speaking the sum doing that, right? This is the sum, A equals to the sum. So making the dot product is doing that. This is delta Mn. So this is going to be, there's only one term, which is Am. So Am equals to the projection, or the dot product with one base vector. So we can use the same concept in the function space. We can expand the function, but now we have lots of eigenfunctions, right? You see that in practical case, the index goes from 0 or from 1 to infinity. I have an infinite number of functions. So it would be an m-dimensional space with m going to infinity. So I can use the same concept. So the question is, to what extent can I approximate a function of domain by an expansion of orthonormal functions? So I build the error, which is can be defined, okay, by the difference between the function and its approximation squared. Why squared? Could be just the absolute value. But square is better because absolute value has discontinuous derivative. If you square that, you lose the discontinuity. So you can do that and minimize this error. I mean, you integrate with the weight function because weight function always appears in the definition of integration, cross integration in the domain. So you minimize this error. If you minimize the error, it means that you want to ensure that the derivative relative to the mth coefficient is equal to 0. If you work that out, you find that the coefficient is given by this. Minimization of the error gives this solution to the problem. Okay? Right? That's what it should be. We say that the expansion converges to f on the average. I mean, you guys are going to simulate this on the computer, right? With an expansion, you find the number of terms, see what happens when you increase the number of terms. We'll do some simulation of that. But what I'm saying is that if you have some function, some funny function here, that has, for instance, that might have a discontinuous derivative. Let's say, function that's constant that suddenly goes to 0. This is b equals this is b, right? And this is a. That's the domain a equals 0. A function 0 then goes like this, goes back. Constant function, right? If you approximate by a certain expansion of orthogonal function, you're going to have something like this sometime. As you put more and more terms, you're going to have a sudden change here. And you start getting, the expansion is converging to the function on the average. We are going to have problems in discontinuous derivatives sometimes. But recall that physical functions, in general, they don't have discontinuous derivatives. Physical things, they are continuous. Okay? I mean, this table ends here, but if you go macroscopically, it's going to have a continuous transition until it goes from wood to air. Okay? It's that way. And you always have some fast change, but not discontinuous. You always have a continuous change.
Notice that you can say by increasing the number of
but rigorously, those functions that you use, they are always 0 on the edges. And this original function has two values, or 0 or max. So this is not a physical function. That's two values, right? That's one value only. So you can try to approximate those non-physical things by physical things. You're going to have some problems on the edges. You're going to have some spikes on the edges. Gibson phenomenon, which is known in Fourier series expansions. So that's why you say that, you notice that computationally, you cannot use an infinite number of terms. You have to use a finite number. So when you do that in computing, you have to use a criterion to stop the expansion. You have to do some logic there. So when you increase, it's expected that if you increase more and more until you get to infinity here, you get f equals to the expansion. Okay. So this was obtained by minimizing the error. We can always simply use the algebra I just made for the vector, make the dot product on each side of the expansion, use the orthogonality between eigenfunctions, and show that the expansion is always given by the same result obtained before. By simply doing the orthogonality of the function, you show the same result. That the coefficient is given by the dot product between self-function and the function that I want to expand. Okay? So finally, to finish this class, and the concept of completeness. How do we write an equation for saying that the set is complete. Well, let's see. That's the function expanded in orthogonal functions of the problem. The coefficient is given by this thing here. Okay. Recall that this is given by right down here. So let's make some, or just notice the indices that appear. So if we have the dot product between UM, which is the coefficient of expansion, is this thing here, and F, this can be written like this. Integral from A to B, conjugate of an integration variable I'm going to call x prime, okay? Variable, because integral between A and B. F of x prime, weight function of x prime, dx prime. When you finish this process, you have something that depends on A and B only, don't depend on x prime. X prime was swept between A and B, right? So when you expand f of x, it's going to be 1 or 0. It might start in 0 here, okay? Depends on the problem. A Legendre polynomial has the index 0, okay? Others don't have. So you're going to have that. So the coefficient is given by this. So I have to put this in here. Times un of this variable here, x. So these are different things, okay? X prime is integration variable, x is the point where you evaluate f. So, if we rearrange terms here, it's going to be something like this. Integration from A to B, okay, of a sum. What's going on? This I hope it's not. Of a sum of of a sum. Let's make it like this. I'm just interchanging symbols here. Of x, okay. Then you have, let me put the double x prime here. I forgot the double x prime. So I have double x prime, you have this sum here, then fx prime, which is here, dx prime, okay? So, I mean, what does the equation say? Says, the equation says that a function of two variables, x and x prime, times x prime, integrating between a and b equals to fx. But we have to remember a unique property of the Dirac delta function, which is fx can be obtained by simply integrating This is a unique property. There's only one function that can do that can reproduce the function by doing this integral, which is the Dirac delta function. It means that this thing here is the Dirac delta function. It's the same relationship. There's only one function that can do that. Okay? So that's what determines the completeness of a set of orthogonal functions. Is this function here, this relation, I mean sorry, put that very large so you can see well, okay? Is this thing here. A complete set of orthonormal functions, UN, is said to be complete and the completeness is given by this relationship. What can we do in simulation? We can simulate this by a finite number of terms and see how this thing gets to become, as you put more and more terms, as this gets to become a very peaked function, okay, at the point x prime. A centrated function, which is 0, otherwise it gets very high, very intense right on the point, on the center, okay? You can simulate that. So that's the completeness. So here I have some examples. Also, I mean, I have a reference here if you want to see more on the theory of differential equations, of self-adjoint operators, emission operators, Sturm-Liouville theory in Atkins, mathematical methods for physicists. They have between chapters 8 and 14. They have between 8 and 14. Have several chapters that talk about this. We don't know more. So here is a set of examples of complete sets of orthonormal functions generated by differential equation. This is the oscillator equation, electronic oscillator, harmonic oscillator equation. We have two solutions. We can make a Fourier series of sines and cosines. Here are the orthonormal functions. Here are the general expansion. Here are the coefficients, and here this is the completeness relationship. However, there's a missing term here that I didn't write, but I should have written. I didn't write because this missing term is 0, okay? But for simulation, it's important. So this completeness, I could write like this. I'm going to write here, so you guys remember this when you do your homework, your assignments. The only change that I will add here is to add a term like this one, replacing cosine by sine. Okay, so the completeness would be something like this. Then it would be something like this: cosine, exactly as in the table, plus sine, okay? Why this second term was not included? Well, this term, if I have an infinite number of terms, this sum, infinite sum, gives 0 results. However, in simulations, you want to simulate the approximate delta function, okay? With your sum is going to be a finite term sum. So we have to use that to see how this thing approaches, right? I mean, this term starts to be irrelevant as, you know, we put more and more, starts to be negligible. But it's going to be important in the simulation. But exact solution, you don't have to use that for infinite set, infinite series. Okay? But for simulation, you have to use that. So we call that.
When we use sine term, it doesn't make any changes in the simulation.
No, it's going to make change. That's why I have to include it. If it's an infinite set, it wouldn't make any difference. But when you put 3 terms on, for instance, this term is going to be important. 4 terms. I mean, if we increase from 1 to 1,000 terms, we have to see the transition. We have to put that term there. So the simulation is going to work if you do that. Okay. This is the example for the Fourier series. We also have Fourier series of complex functions, very important too. Okay. You combine the sine and cosine into a single complex function. Now I have an index that goes from negative and positive integers. And the completeness is something like that. Okay. And so forth. Legendre polynomials. This equation, weight function, the normal function here. This is an L derivative, L order L, okay, of this binomial here. So there's the general expansion. These are the coefficients. This is the completeness relationship, and this is the syntax in MATLAB. Leg of NX. You can find that in MATLAB. Okay. We're going to play with that, so we're going to have to use Bessel functions. So and so forth. So we have a Bessel function MATLAB of zero order. We also have modified Bessel function, but modified Bessel functions are not orthogonal functions. The traditional Bessel functions are. Okay. So we have the zero order is like this. The syntax J0 of X, but the M order has to have is the syntax like this. Have an M inside and have Jn. That's how you write the Bessel function in order in MATLAB. Okay. Okay. The assignments. There's two parts again. First part is by hand, paper and pencil or pen. Several. I want to verify some of the things that are mentioned in these sheets, okay. And verify some of the relationships. Do some expansions. And the second part is a MATLAB simulation. Some of those simulations are similar to what we did in the previous. By the way, there's a mistake here. I just found it. Of workshop 6 here, not 8. Sorry. Let's fix it. This is not there, huh? Let me try to fix in there. Let's see here. I'll fix it later. But this is use the same procedure in the previous assignment, which is not number 8, it's number 6. Okay, to make to compare the approximation of function by its expansion, you have to use a final number term, increase the number term, make a animation to see how it gets closer and closer to the approximation. There are other assignments here to use Legendre, Bessel, Chebyshev, MATLAB, built-in functions to do some things. Another example here to make a MATLAB code to see how the delta functions start to appear using the completeness as more and more terms are added to the completeness relation. So make a finite number, make a frame variable, and make an animation. So let's put more and more terms. Let's see how the functions start to compress and become like the delta function. Okay. And this last part here is important because we want to be able to write orthogonal Bessel functions. And to do that, you have to find the roots of the Bessel function. Okay? Each Bessel function of a given order has a different set of roots. You have to find those roots to plug into the argument of the function. Okay? So you have a Bessel function. Order m, so you have to find the n-order roots of the Bessel function to write a new function like this, km n x. These functions are orthogonal in the interval between 0 and 1, if I'm not mistaken. Just a second here. Yeah. In the interval between 0 is more than x, more than 1. If this is a root, at x equals 0, this is Jm0, which is 0 for m equals 1, 2, etc., and which equals 1 for m equals 0. So Jm0 equals 1 only for m equals 0, for J0. And the Jm of 1, Jm, I mean, if you put 1 here, Jm of x1 equals 1 is, by definition, this is a root, okay? This is going to be 0. So we have, I mean, to build those functions, what we have to do? We have to find the roots of the Bessel functions. So the two final items in this assignment are to make program blocks to determine the first n roots of a Bessel function. Okay? So you do that to build orthogonal functions. Okay? There's some suggestion how to do this here, some logic. So I have to study this thing and see how to do it. Okay? So when you find, I mean, when you make a program block to find any roots of Bessel functions, then you are prepared to write orthogonal functions. You can write according to this prescription. Right? You're going to put in the root here and build the orthogonal functions. So using those, you're going to do some exercise, some expansions using Bessel functions, and see that it works. For instance, you can expand a function in the domain between 0 and 1. Suppose you want to expand a function f of x. I'll just put some explicit example. For instance, as expansion of zero order Bessel functions. It's going to be something like this. Finite expansion. Should be infinite, but I mean, you cannot do that completely. So you're going to have AM. Something funny is. Sorry about that. What is it? There. There. Keep sliding up and down. I have to find it. No size. So you're going to expand it as a zero order. So we have to find the first n roots of J0. So that's one type of expansion. But you can also expand as a function of J1, for instance. So there's going to be a different set of roots. Okay? Let's say Q1, because the roots of the Bessel function are the one, and I'm sorry, this is supposed to be n. Okay, sorry about that. N here. All of this is n. Sorry about that. J1 n of x. Okay, so we can expand with two different Bessel functions. Okay, but in this case, there's a set of roots. In this case, there's all the different set of roots. We have to find a way to do that. Okay. So that's what was going to be the assignment, and that concludes our lesson for today. So Friday I'm going to be available, so we can discuss any pending assignments, and this is what any of you start doing this new assignment.
It's too large.
Huh?
It's too large.
Yeah, so we have to return it by 9 days, let's say, in principle. Theoretically, in 9 days. You know, next Friday. 9 days from today.